Hi everyone, we're Team No Plan with me, Ryan, and Ben. And we're here to talk through our code and implementation for Lab 3. So for the first part, we worked with this file that you can see here, matrix_cpu.c. So the very first code was actually given. The function is a matrix multiply on the CPU. So you can see for each row of A, each row of B, we calculate the results and store it in the matrix C. And then if you don't mind scrolling down a little bit, we can see like the main code here. So first we get n, which is the user input as like the matrix size. We allocate space for each of the matrices and initialize them in that for loop. We start the timer where the comment says start the timer, just to time how long the multiplication takes on the CPU. And at the very end, we just like free up the memory from the platform. So that is this code file. I believe next is matrix_gpu.cu. Okay, perfect. So similar idea with the matrix multiply function. And then now if we look through our main, again, it's just sort of like how much memory do we need? We allocate that memory on the CPU, fill the matrices with random values. And then the thing to note here is the GPU can't access CPU memory directly. So where you see on lines 45 and 46, CUDA, MEM, CPY, we're copying those matrix from the CPU to GPU. And then after that, we're doing like parallel execution on the GPU, which is a nice benefit. We're timing everything. And then on line 61, we're running that core function matrix multiply GPU, waiting for it to finish, seeing how long it takes. And then, like always, at the end, line 75, just freeing up all of our memory.
Okay, and that leads us towards part four, which is the optimized CUDA version using memory tiling. So a lot of this is based on the template provided. The main function looks a lot similar to what Ria just described for the other implementation. But what we did here is we implemented a version of memory tiling. So using shared memory that is accessible only towards a block. And by using shared memory instead of unified memory, we're able to save a lot of time. It's just much faster compared to the naive CUDA implementation. And this implementation is kind of very similar. We're computing the row, the specific index based on our block ID and our thread ID, and then using that to loop over a specific number of tiles specific to the block index, the row and column that this specific thread is going to be working on. So as you can see, it's doing this partial dot product stored in this p-value accumulator, and then syncing threads in order to make sure that everything is lined up at the end. And the results are included in our lab report where we can see that this tiling implementation is much faster compared to definitely the base CPU C version and as well as the naive CUDA version. So the speed up compared to the base C was about over 1,000 times of speed up compared to that 2048 sized CPU version. And we also saw a pretty around a 1.5 times speed up compared to the naive CUDA, which was still a lot of a performance boost. And then next, after this, we went and implemented the cuBLAST version using the cuBLAST library. This was pretty straightforward, but essentially it's handled all through the library using cuBLAST SGEM. And there's a lot of linear algebra optimization that's happening here that NVIDIA CUDA took care for us. But this also led to a kind of substantial speed up where even above what we did for the optimized GPU version, this one even went faster based on a lot of the efficiency, the lower overhead, a lot of the optimizations that are made within the CUDA library.
Yes. So this is sort of taking the code that Ryan had talked through, building off of it to create our own library, which I believe is accessible later on in this function. Yeah, so we have a wrapper function here. And then eventually that creates a sort of shared library that we can use in Python. And then also if you go into a report for this section, you can see some of our answers comparing the different methods, the different matrix sizes, etc. And I'll hand it back to Ben now for part two.
Yeah, thank you, Ria. And as Ria mentioned, that shared library is also actually where my work for the part two convolution lives as well, since we were instructed to add it to the convolution itself. And let me go ahead and start screen sharing. Okay, can you guys see it?
Yeah.
Okay, so I'm gonna show off the file that I was working on before I actually moved it into that shared library. So my part was about comparing convolution on the CPU versus the GPU. And the main difference here is that for the CPU, it's going to be a lot slower, and that's because we don't have as many threads, nearly as many threads as the GPU, and the GPU is able to actually take advantage of how many threads there are and the parallel processing because there's an increase in the number of threads to have significant speed ups. The specific numbers are listed in our report, but here is the code for the CPU, and then above is the GPU logic. And just like Ryan had mentioned earlier, it's all about calculating which pixel correlates to which thread since we have so many threads. And we want to make sure that each of them is responsible for, you know, a certain pixel to take advantage of the parallel processing. And yeah, what I have down here is more of what everyone's been discussing, copying the data from host to device since we need to pass it from the CPU to the GPU. And also back again from the GPU to the CPU for the final output. And also, a big part of mine was actually trying to test it on different images. So, in specific, I tested an edge filter. I put it more explicitly here in this file, but basically, I was testing different filters and different dimensions. So, first of all, is the edge filter, and you can see that it's only positive in the center, the rest are negatives. Thus, if something has, edges, right, it's going to be amplified. And this was seen in our photo output as well. Same thing for the 5 by 5, 7 by 7. I also tested horizontal line filters that were detecting horizontal lines, and then a vertical line filter as well with the large positive numbers going up the vertical. And yeah, overall, with our report, the outcomes that we saw were pretty much aligned with what we expected. Comparing the direct CUDA to the CPU, it was much faster. When we put it in our shared library and called it via Python to the CUDA function, that was a little slower than the direct CUDA, but still faster than the CPU, and still overall very much worth it. And I thought this was a really interesting lab because it kind of connected to the fact that labs out there like or libraries out there like PyTorch rely on similar architecture where we're using Python to call all these functions, but underneath the hood it's really C and CUDA, and it goes to show, as Professor Cho always mentioned, the value of learning CUDA over Python because a lot of these machine learning libraries rely on it underneath the hood. And yeah, just for the final reflection section as well, GPU scales much better than the CPU as image size increases. And this kind of aligns with what we expected because as the pixels increase fast, then we need to make sure that the GPU is scaling as well. And the overhead with the GPU, we need to take time to transfer from the CPU to the GPU for all of the initial image data, but generally takes less time when compared to the computation of everything with the convolution. And yeah, overall, that is about it. All of the specific graphs of the speeds and all that are in our report. But yeah, thank you.